Hello guys, welcome to Self-Help Maths Academy. Today we're going to talk about the continuity at a point. So what do you mean by the continuity at a point? So let us see the first definition. A function say f from a to a, f from a to r is said to be continuous, is said to be continuous, okay, at a point, say say a belongs to r, a belongs to the set A if for a given epsilon greater than 0, however small, this is however small, say there exists a real number, there exists a real number delta which is greater than 0 such that f of x minus f of a is less than epsilon, okay, whenever your x belongs to a and difference between x and a is less than delta. Okay, so what do you mean by this? So this means that your function, your in like in short, the continuity mean without lifting, if you're able to draw a graph, without lifting, if you're able to draw a graph, okay, without picking up your pen, if you're able to draw a graph, then we say that is a real meaning of a continuity. So if you have anywhere break, for example, I want to draw, there is one graph, say I have a graph like this. Okay, if you see, I can't draw this graph without lifting my pen. That means this function is what? It is having the discontinuity. It is having the discontinuity. So whereas this function I can draw without lifting my hand, right? So the basic meaning of that continuity is that. So here we are discussing the continuity at a point. So to do that, what we are trying to understand here is we're trying to pick up the function from a given set A to R. Okay, so we say that this function is continuous at a point A. So here the function is there. We have a function which is from a set A to R. Okay, we say that this function is continuous where I'm taking any point, say A. This point A belongs to A. Okay, and such a way that there is a given epsilon greater than 0. However small, there is a real number delta such that, so if I take a point, say x here, okay, any point x here, then it will give me f of x. If I take a point A here, it will give me f of A here, right? So in such a way that there is a epsilon, which is a small positive number, and with respect to this positive number, there exists a real number delta, such a way that you can see the difference between these two, that is f of x minus f of A. So difference between these two elements should be less than epsilon. This should be less than epsilon. Okay, this should be less than epsilon whenever your x, as you see, this x is belongs to A, the difference between this x and A, this difference between x and A, if this is less than delta, the difference between these two is less than delta, and the difference between these two is less than epsilon. If this condition satisfies, then we say that the given function f is continuous at a point A. A given function is continuous at a point A. So in other words, we actually try to express this in terms of the equivalently in terms of this way. Let me tell you that. Let me okay, so in this, equivalently what we do, we'll try to see in the, let me take the other Okay. Okay, let me click on this. Yeah. Whatever. Mhm. Mm. Okay. So the other meaning of the equivalent definition of this particular like notation is, so when we say that this particular continuity will be having the equivalent form of the notation. Let's see how do we say that equivalently a function is continuous at a point. So here what we do is, let us consider the given function, say f of x. F of x, it is continuous. It is continuous at x equal to a. Okay. If and only if and only if the limit of f of x as x is tending to a is equal to f of a. So if limit of the given function as x is tending to a is equal to f of a. So this is possible. This is possible if and only if the limit of f of x as x is tending to from left hand side, this is equal to right hand side, say x is tending to a plus, if both from left and right limit exist and they're equal to f of a. So this is very important condition. So we say that a given function is continuous if limit of f of x as x is tending to a is equal to f of a. So in order to say that limit exists, there should be a left hand limit and the right hand limit. They should exist and they should be equal to f of a. Then we say that the given function is continuous at that point. Okay, so that is very important. Now similarly, uh, we have got a continuity. We have got a continuity, say we will discuss about the continuity in the interval, like in an open interval. So when we say that the given function is continuous in the open interval, so a function here, a function, say f is continuous. F is continuous in an open interval, say in an open interval, say open interval AB. Let us take this way. If f is continuous, f is continuous at every point of the open interval AB. Okay, that means what? If at every point of this open interval AB, okay, if at each and every point of this open interval AB, the given function f is continuous, and we know that when we say that a given function is continuous at a point, so if these conditions are satisfied, we say the function is continuous at one single point. But in this way, at each and every point of this interval, if the function is continuous, okay, then we say that the given function is continuous in an open interval. And f is continuous in an open interval AB if and only if for every point C belongs to the open interval AB, such that limit of f of x as x is tending to C should be equal to f of C, where the C is what? C is any point in the open interval. Like if you see, your open interval like contains the infinitely many points, as you know, so that if you take any point C here in between this, so it should be continuous at every point of this open interval. If that is satisfied, then we say that the given function is continuous in the open interval. Okay, similarly we also have the discuss about the continuity on a set. Like for example, like now we have discussed about the continuity at an open interval, continuity at a point. So similarly, we also say that the given function will be continued at a open interval. Let's see how do we check that. Now, in order to understand the continuity in an continuity at a given set, what do we mean by that? Say a function say a function f is said to be continuous. It is said to be continuous on an arbitrary set. Let me take an arbitrary set, say yes, which is a subset of R. Okay, if for each epsilon greater than 0 and for every element, say A, belongs to S, there exists a real number. Say delta, which is greater than 0, such that the difference between f of x minus f of A is less than epsilon whenever your x belongs to S and the difference between x minus A is less than delta. So I think equivalently we have seen this the function we have. Obviously this should be from S to R. So we have function from S to R. So where S is a subset of R in fact. So we are taking any element, say A. This is element A which is belongs to the S. Then there exists epsilon and delta greater than 0. These are positive numbers. So as you know, for A we have a mapping which is like say f of x. So we have f of A here, sorry. So for x, we have say f of x. All right. So then the difference between them, that is f of x minus f of A, this is less than epsilon whenever the difference between this x and A is less than delta, where x is belongs to S and A is belongs to S. If this is true, then we say that the given function f is continuous at an arbitrary set S, which is a subset of R. Okay. So now let us try to understand this particular, concept with the help of examples. So how do we do the examples here? Okay. So let us try to understand with the help of example. Now, the first example is say by using the epsilon and the delta definition. Okay, we use the epsilon and delta definition, and we prove that the first one. Let me take the simple one. F of x is equal to say 3x plus 1 is continuous. Continuous at x equal to 2. Okay, so let us see what do we mean by this when we have to understand that the given function is continuous at a point or not. What are the steps we have to check? So here let's start with the solution. We will write a solution here. The solution goes like this. Say here what is given is here f of x is equal to 3x plus 1. Okay, so as you know, I told you the equivalent definition where I've told you that we need to check the given function at the given point, and like where we have to prove that as continuous. So we need to find out that a limit of the given function at that particular point, whether it is equal to the limit of the point or not. So for that, what I'll do now, here f of x is equal to 3x plus 1 is given, and at x equal to 2 we need to find out whether it is continuous or not. So therefore let us find out the function at that point, f at the point of 2. So f at that point of 2 means wherever x is there, put 2. You will get here 3 times of 2 plus 1, which is equal to 7. Okay, so now let epsilon greater than 0 be given. Okay, this we have to take. Let epsilon greater than 0 be given. So what is the condition? We have the condition that difference between f of x minus f at the point of 2. Here my A is 2. So at the point of 2. So this should be equal to, let us see what is this. F of x is 3x plus 1. And f of 2 we have found that is 7. So this is equal to 3x minus 6. So simply I can just write 3 out. This will be x minus 2. So since 3 is a positive number, I'll just take it out here, x minus 2. Okay. So it is 3 into x minus modulus of x minus 2. So this is less than epsilon as per the definition, right? So whenever, okay, so whenever, if you see, it is like, say, in place of x minus a, I have here x minus 2. Whenever, you can see, just write it in terms of 3 into x minus 2, which is less than epsilon. Okay, so that is nothing but what? That is nothing but, if you see, your x minus 2 is less than, I can write this as this 3. On the other hand, it will become epsilon by 3. Now, if you observe carefully, this one is like x minus a. This one is like x minus a, and this is like your delta, if you observe. Okay, so therefore, now what we do, we choose our delta. Okay, we choose that, like, if we choose our delta should be equal to, in place of delta, I have here what? Epsilon by 3. So if we choose our delta is equal to epsilon by 3, then if you observe carefully, this is the difference between this and this is less than epsilon. That's what we have achieved here. Then difference between f of x minus f of 2 is less than epsilon whenever your x minus c, in place of x minus c, you have x minus 2 is less than, I'll write here delta, because I have chosen this as our delta. Okay, less than delta. So this is nothing but the definition of a continuous function, right? This is nothing but a definition of a continuous function. So therefore, we can conclude that f of x is continuous. F of x is continuous at x equal to 2. X equal to 2. Okay, so basically we have to have these steps in order to understand whether the given function is continuous or not. Here we are using the epsilon and delta definition in order to prove them. Okay, let me take another example. So let me take another example here in order to prove this. Okay, quickly, yeah, the second example, maybe, yeah, f of x is equal to, say, um you have got x square minus 4 if x is not equal to 2, and it is, say, x, it is equal to, say, 4. Let me erase here. It is equal to, say, 4 if x is equal to 2. Okay, so it is continuous. We have to show that it is continuous at x equal to 2. Okay, all right, let us understand this function first. So that means this particular function is defined as x square minus 4 if x is not equal to 2. So at x equal to 2, this function will take the value, say, 4. That's the meaning. And we need to prove that this particular function is continuous at x equal to 2. So for this, let us start with the method. What we have first. So given that your f of x is x square minus 4, okay, and x square minus 4 upon, sorry, this is actually, sorry, here I have missed one more, divided by, let me add it, it is incomplete here. Here I have x square minus 4 upon x minus 2, and this is, let me erase this also, and it is taking the value 4 if x is equal to 2. Yeah, this is the function now. So now this is all right. This is x minus 2. F of x is given as x square minus 4 upon x minus 2 whenever x is not equal to 2. And as I have to prove the given function is continuous at x equal to 2, therefore let me find out what is our f at the point of 2. So substitute the value, given that f of 2, f x at x equal to 2, the function is 4. That is given. Okay, it is given. Okay, I'm not substituting here. You should not be confused that if I put x equal to 2, it will be 0 by 0. No, because at x equal to the 2, they have given the function as 4. So that's what I'm taking here. Okay, so now we know that let epsilon greater than 0 be given. Okay, so we have to start with our method. then we know that difference between f of x and at x equal to 2 we need to define. So this is f at the point of 2. This should be equal to. So what is our f of x? F of x is x square minus 4 upon x minus 2 minus f at the point of 2 is 4. Okay. So this is equal to. Now if you take the LCM, before taking the LCM, this is nothing but like in the form of, here if you see this quantity is in the form of a square minus b square. I can write this as x square minus 4 can be written as x plus 4 into x, sorry, a square minus b square, x plus 2 and x minus 2. So you know that a square minus b square will be a plus b into a minus b. So therefore we can write this as, here we can write this as this, we can write it as x plus 2 into x minus 2 upon, this is x minus 2 here, and this is minus 4. So I can cancel this x minus 2 with this, and then I'm left with here x plus 2 and minus 4. Okay, so this is basically what we have left with. We have left with x plus 2 minus 4 will be x minus 2. Okay, so this I can write it as here. I have got here x minus 2. So this is less than epsilon, because we know that the for the condition f of x minus f of 2 is less than epsilon. So we got x minus 2 less than epsilon. So here if you observe this one, this is like x minus a, right? So this we have to write whenever our x minus 2 is less than epsilon. So here if you observe in place of delta we have got epsilon. So therefore we have to choose our delta as epsilon. So this choosing is very important, like depending on how you got in previous case, you have got your delta as epsilon by 3. In this case you got your delta and epsilon are one another same, right? So that's how the choosing will be, depends on the different problems. Okay, so then now we got choosing delta is equal to epsilon. So therefore f of x minus f of 2 is less than epsilon whenever x minus 2 is less than delta. Okay, so this is less than delta. So this is nothing but again the definition of the function to be continuous at a point. So hence what we say that f is continuous. F is continuous at x equal to say 2. Okay, so this is another example where we are trying to understand the given function is continuous at a given point. Okay, now let us take another example. So here, in order to understand the let me take the third example. In this example, here they have given you f of x equal to say x cube minus 1 upon x square minus 1. This is defined as, this is f of x cube minus 1 divided by x square minus 1 if x is not equal to 1, and it is equal to 3 by 2 if x is equal to 1. And we have to show that it is continuous at x equal to 1. We need to show this one. Okay, let us try to see now. To get a solution, what we do, we have to prove that the given function is continuous at x equal to 1, and they've given you that your f of x is equal to x cube minus 1 upon x square minus 1. Okay, here basically this is true where when x is not equal to 1, and your f at the point of 1 is given as 3 by 2. Okay, so this is given as 3 by 2. Now for let epsilon greater than 0 be given. Let epsilon greater than 0 be given here. So when it is given, you know that difference between your f of x minus f at the point of 1 we need to consider. Now this is equal to f of x. This is your x cube minus 1 upon x square minus 1 minus f of 1 is 3 by 2. 3 by 2. Okay, so here basically if you observe, this is like in the form of a cube minus b cube. Let me write this. Yeah, so here this is like your x cube. Let me use the different color. You have got x cube minus, sorry, I'm just I'm trying to write this x cube minus 1 in terms of a cube minus b cube form. So which is equal to a minus b. So here a is x and b is 1. A minus b into a square plus ab, that is x into 1 is x, plus b square, that is 1. So this will be like in the form of a cube minus b cube, which is written as a minus b into a square plus ab into 1. So a into b, if you can write 1 into x, that is simply x, right? So let me write this way, which is equal to, I'll write this as x minus 1 into x square plus x plus 1 divided by a square minus b square. This we can write as x plus 1 into x minus 1. Okay, and this is minus 3 by 2. So here we can cancel this x minus 1 and x minus 1. So you also use if you want, you can just use the like LCM here. So, and you can just rewrite this as 2 times of this one and 3 times of this one divided by 2 times of this one. So which we will be getting as, if you see, 2x square plus 2x plus 2 minus 3 upon 3. Okay, sorry, this one minus 3 into x plus 1 divided by 2 into x plus 1. Okay, simplification. 2x square plus 2x, here minus 3x will be minus x, and plus 2 minus 3 will be minus 1. So the final answer I can write here as, so this I will get 2x square, 2x minus 3x, which is minus x here, and minus 1 upon, this is 2 into x plus 1. Okay, all right. Now let me take this one. Let me take this one, say 2x square minus x minus 1. After multiplication, I should get negative 2. After addition or subtraction, I should get negative 1. So after multiplication, negative 2. After addition or subtraction, negative 1 is minus 2 and 1. If I write this one, I will be getting here, just write, see, 2x square minus 2x plus x minus 1 divided by, this is 2 into x plus 1. Sorry. So this will be equal to, here what we take, here we can take this 2x out, here we're left with 2x minus 1, and here if I take a 1 out, it is x minus 1 upon 2 into x minus 1. So this is equal to, so we have got the factors as 2x plus 1 and x minus 1 upon 2 into x minus 1. So all right, this x minus 1, x minus 1 also we can cancel. So now we are left with what? We are left with, this is equal to, we are left with is equal to 2x plus 1 upon 2. Okay, so this is what we have left here with. So this is 2x minus, oh, I think we did a mistake. This one should be plus 1 here. So please make a corrections. So here what we have got is not this one. Let me rewrite. So that means we have to be careful with the signs here. 2x plus 1 is there. So this should be 2x plus 1 and x minus 1. And this one is 2 into x plus 1. All right. This is what we have here. So this is the basically, now from here what because here it is containing 2, this also has a coefficient as 2. What I do is I'll just take this x minus 1 out, x minus 1 as out in the modulus, and also we have left with here 2x plus 1 upon 2x plus 2. Okay, this is what we have. So this as you know that this is 2x plus 1 divided by 2x plus 2. This quantity is still less than 1. So therefore this quantity and this quantity into this quantity, this will be still less than what? Modulus of x minus 1. If you want, you can write here, since modulus of 2x plus 1 divided by 2x plus 2. Obviously 2x plus 1 is less than 2x plus 2. So if you divide any small number by the big number, obviously you'll get this number as what, less than 1. So this quantity is less than 1. Less than 1 into this quantity is still less than what, x minus 1. So this is what we have got. So therefore this is nothing but this we got as less than epsilon. Okay, we started with what? Now if you observe, this is like x minus a less than epsilon. So we started with this one. We started with this one and we got it as less than epsilon. So therefore now what we do, we choose our delta as epsilon. Okay, delta as epsilon. Therefore we got a conclusion that our f of x minus f of 1 is less than epsilon whenever we have got x minus 1 is less than delta. So this is nothing but again a definition of a continuous function. Therefore conclude that continuous f is continuous at x equal to 1. Okay, so this is how we say that the given function is continuous at a given point, say x equal to 1. All right, this is another way of uh, showing that the given function is continuous at a given point x equal to say 1, 2, 3, whatever the given points they'll ask you for. Okay, so now maybe I think I'll give you one example to try for yourself. So just get back to me with the solution. Examine whether the given function, say I'll give you f of x equal to say x cube minus 8 upon x minus 2 at x equal to 2. Whether this function is continuous or not, please check this and uh, comment in the box so that let me see whether you'll get the continuity or not at the given point. Okay, so I think in this video only this much. Maybe in the next video we'll be discussing about the discontinuity and the types of the discontinuity and so on. Okay, so till then I think take care guys, see you all in the next video. Please comment if you have any doubts or anything. Okay, all right then, see you all in the next video guys. Bye bye.